Morning, everyone. My name is Sercan Gül. I'm a PhD candidate from the University of Texas at Austin, and I'm a drilling engineering intern from Pioneer Natural Resources. The subject today is predicting downhole tool failures using Adams drill. Supervisors are Chris Mullin, Ben Potash, and Austin Jeski. A little bit about me. I was born and raised in Ankara, which is the capital of Turkey. You can see a nice picture of my hometown on the bottom left. Currently a PhD student at the University of Texas at Austin, and I will graduate in 2 years. And I also worked as a drilling engineering intern at Pioneer Natural Resources, and my contact information is also provided here. Here is the outline of my presentation. First, I will introduce the tools, datasets, and programs I used this summer, and then I will show some statistical analysis and simulation results, and then conclude the presentation. Assembly, BHA in short, is the common name of all the tools that we are using between the drill bit and the drill pipe. Each tool in the BHA serves a different purpose. Our drill bit, which is drilling the formations, motor, which is used to improve drilling performance and give us the ability to have inclinations in the well, and the measurement while drilling tool, which provides us information about where we are in the well at a certain time. Tools where we see most of the failures happening. In that case, we have to trip out of the hole, change the tool, and trip in the hole again. Parameters that lead to drilling dysfunctions, which include BHA or tool design, the drilled formations, and operating parameters. Functions create many problems associated with revenue. Most common problems are drilling tool failures, non-productive time, and slow rates of penetration. When a tool failure happens, we mostly don't have a consistent method to understand why the failure happened, how to replicate it, and how to prevent it for the next time. The failures happen due to some dysfunctions. The video here explains the vibration modes of a bottom hole assembly. The first example is the axial vibrations happening on the Z direction. Lateral vibrations are the vibrations happening on X and Y directions. Torsional vibrations are the ones on the radial direction. Some events that generate these vibrations can be stick slip, where the bit is sticking, and then due to the excessive force, it starts slipping. Also have bit bounce events, which generate a lot of axial vibrations, the vibrations on the Z direction. Whirl events also generates lots of lateral vibrations. This is how we should be drilling. This is what we should try to eliminate. All these vibration modes and dysfunctions can result in the failures of MWD tools or mud motors. I worked with 2 different datasets from Pioneer. First drilling parameters were obtained from Payzone. Payzone is a company who has various sensors in our drilling rigs and can send us all the service data in real time using WithSemal servers. It is available at a frequency of 1 Hz, meaning that we have 1 data every second. And in some wells, we have recorded downhole measurements using Lodestar downhole measurement subs. We can record the vibrations, torques, and loads happening down the hole, but it's not able to send this data to the service in real time. Data was available at a frequency of 50 Hz. One of the challenges on working with these 2 datasets was the difference of timestamps. Where the downhole subs have a timestamp called as a Unix time, and Payzone had the timestamp of standard days and hours. They were in different frequencies. Therefore, I had to prepare some Python scripts to make these data match in the timestamps and frequencies without losing any information, so that I can analyze them. I performed some statistical analysis. 27 BHA runs where Pioneer used the downhole measurement sub. There were 7 failure cases, where 2 of them happened in the intermediate and 5 of them happened in the lateral section. I performed some calculations on them, such as the cumulative X, Y, Z accelerations, the threshold sums, meaning the cumulative value is above a certain threshold value, the cumulative bending forces, and the tortuous index to try to correlate them with failures. Two examples from the results where the threshold sum of x accelerations above 2.5 g have provided a clear indication in the failed BHA, shown on the left figure. Similarly, for the BHA runs with 8 3/4 diameter, we have seen high bending moments on the wells with failures. In these graphs, the BHA runs showed in red boxes have experienced either mud motor or MWD failures. With Adams, let's introduce what Adams drill is. Adams is a program developed by MSc Software. It's a physics-based multi-body dynamics model, which is widely used in aerospace and automotive industries. To implement the same technology to drilling operations. Here's an example result from Adams drill, where we are modeling a highly tortuous well, which is resulting in stick-slip dysfunctions. On the right are from two different points, where the sub 1 is between the bit and the motor, and sub 3 is between the motor and the drill pipe. It is designed to be used with only the inputs from surface parameters together with characterization of each BHA equipment and survey data to provide information about the BHA dynamics such as downhole weights, downhole RPMs, downhole torques, bending moments, and vibrations. Pioneer and MSc have concentrated on R&D and validation to develop this program. We had no understanding of how to implement this in Pioneer's workflow. There was no consistent calibration method, and there was a very limited amount of case scenarios. I will present in the upcoming slides. Was to figure out how to calibrate the models. In addition to the video, you can see that we are able to model different states of a drilling operation after a connection. What I do here is I circulate the fluid and only rotate the bit. At this point, I tune the bit gauge friction. Afterwards, I introduce the surface RPM, and now I have a dynamic situation, so I'm tuning the whole dynamic friction and viscous damping. Bottom, and started drilling, I'm tuning the bit face friction parameter and increase the depth by 1000 feet of increments. Something that wasn't done much in this program as we didn't have a consistent method of calibration. I'll show you some results from one of the wells. We are drilling an 8 3/4 section hole. There's a 958 casing set at 6,130 feet. 2/4 hole is going to be drilled vertical and curved sections. We also have downhole measurements obtained from string subs, so we can compare the Adams results with the downhole measurement subs results. Motor failure happened in this case at 13,000 feet. Here are the results from the first. Here are the first model results. Top graph here, I'm showing you the comparisons of downhole torque measurements in the Lodestar downhole measurement sub and Adams simulation results. On the bottom graph, I'm showing you the Payson results of surface torque compared with Adams surface torque results. Blue lines on these graphs are showing the Adams estimated results, where the red ones are the real measurements. You can see in the beginning we have a very good calibration in our model, and at 8,300 feet, our data in downhole torque and surface torque are matching very well. Here's the depths, and when we come to 10,000 feet in this case, you see some deviation, some discrepancy happening on the results with the measurements coming from either Payson and Lodestar. When we introduce 20% of bit degradation into Adams model, we are starting to get a better match, which is shown with the black lines here. When we come to 12,000 feet, in this case, again, only using 20% of bit degradation is not enough to explain the data. Therefore, using Adams, we also introduce degradation. You can see again, the black line is matching the red line better, introducing the motor degradation. And this is an example where Adams is warning us that some motor degradation is starting to happen. It's actually more than 1,000 feet before the failure happens. And when we come to 13,000 feet, in the previous example, we had 20% of motor degradation, and in this case, we have to introduce 30% of motor degradation to make this data match. Example from the same well on what could have been done differently. So that there were high bending moments in this bottom wall assembly. It have caused the failure in the long run. If we were to have a motor with a lower bend angle, Adam says that we can decrease the bending moment significantly. In the graph that I'm showing you, the red line is the bending moment results from Adams using a low angle and low bit to bend ratio motor, and the blue is the high angle motor. By the way, I have to note that I'm not suggesting here to use a 1-degree bend motor in a curve section, but this is just an example of how different mud motors can be designed using Adams drill, and the results can be investigated. Here are the results from a different well. In this case, we are drilling the vertical section with 12.25 bit. We have a 1338 casing set at 1463 feet. And again, we have both the surface and downhole measurements available, so we can compare our model results, real-time measurements. Mud motor failure happened at 5,800 feet. Similar to the previous case, in the beginning I made the model at 1400 feet. And again, the downhole torque measurements are shown on the top graph and the surface torque measurements are shown on the bottom graph. And as you can see, comparing the Adams results with either Payson or Lodestar measurements, we are having a very good match. Increase the dip depths a little further to 2000 feet. Again, we are having a very good match with the and the measurement result. We come to 4000 feet, we are starting to see some discrepancies happening on the surface torques, but our downhole torques are again quite accurate. I've only been drilling for around 2000 feet, so there is no failures yet. When we increase the depth to 5000 feet, however, something happened between 4000 and 500, and now we have some discrepancies happening between the blue line and the red line. And in this case, we have to introduce 30% of motor degradation to make the model results match with the measurement results. To investigate why this motor failed, I prepared 9 models using Adams drill with different surface drilling parameters. Our parameters were 45 pounds of weight and 75 RPM of pipe rotation, which is shown on the bottom right. The red line is the motor RPM, which is the rotation generated by the motor, and the blue data is the torque generated by the motor. Notice the line shows how the motor RPM behavior should look like. In our case, we were drilling over the limits of the mud motor and resulting in motor stalls. Adams can tell us in these cases what we should change to eliminate the failure from happening. For example, if we went to the case in the middle with surface weight on bit of 30 kPa and surface RPM of 50, we would have eliminated the stalls from happening. Failure would have been eliminated as well. The question is, why did we give too much weight on the motor? When I investigated the data further, I noticed that we had lower surface weight measurements than the downhole weights, which is actually physically impossible. Which means that there was an inaccuracy at the surface weight measurements, resulting in too much downhole weights in the end. Therefore, we passed the operational limits of the motor and result to motor stalls, which in turn results in a failure. I have shown 2 different examples of how Adams can warn us as soon as the failure starts. It's very important to change something to be able to see the effects using a simulation before it ends up being an expensive failure. In some scenarios, we might be able to see a dysfunction starting to happen and fix it by changing the operational parameters. If the case is too bad and the motor is getting worse and worse, we can trip out of the hole before the tool fails. Eliminate the lost in hole, fishing, and sidetracking costs. I also worked on the scalability. The question was, can a calibrated for an offset well be used in another well at a different path with high confidence? For example, if I want downhole measurements from one location, can I use those measurements and generate a digital twin with Adams for the wells in other areas? So I compared the tuning parameters using 3 different models So that the same constants were used in all three of them. This is actually very good because it seems that we do not really have to worry about these tuning parameters in the model a lot. The program still needs downhole measurements from several wells in each area to make sure that the models are accurate, and 1 or 2 full-time subject matter experts to run the models and evaluate the results to generate value in a company's workflow. The presentation is that the main problems in the studied BHA runs were high vibrations due to stick slip dysfunction as well as high downhole torques. Using atoms, we have verified the accuracy, implemented the progressive validation method, and presented successful use cases. The validation work was already completed, and with this slide I show the details of calibration method and case scenarios. Future steps, MSC and Pioneer are working on field trials, implement the technology in real-time operations. With that, I would like to thank you all for your time and attention, and thank to everyone else who has supported this project. We can answer your questions now.
Right. So, so let me start with the questions. I see a few questions streaming in. So, Sarjan, I think you kind of spoke about this at the very end, but the question is Adam's drill a real-time simulation tool?
It is not a real-time simulation tool right now, because running the tests and making the calibrations takes some time. But I believe this is something MSC software is working on.
I can add a little context to that. So part of the issue with running in real time and basically keeping up with the drill string is the amount of time it takes the solver to solve the equations of motion. And we're talking about thousands and thousands of equations at each time step. And so obviously, if you have a shorter drill string, it's going to run faster. The shorter drill strings, depending on how you set up the model, are, you can run 10 minutes of simulation almost as fast as you can run 10 minutes of drilling. So it's pretty close for short drill strings. The longer you get, especially out in the lateral drill strings, it takes considerably longer just because there's so many more moving parts and so much more solver overhead. But we are working on that. Solver speed is one of the critical things that we want to deal with. Even at that, we're talking about for a 3D model with lots of contact, we're still talking about simulations that run in less than an hour for, let's say, a 12 or 13,000 foot drill string. So that's not too bad.
Okay, all right. Thanks, Jennifer. Thanks, Sarjan. The second question is maybe on a related topic. So the question is, what is the level of predictive capability in Adam's drill? How intense is the calibration process?
Jennifer, do you want to answer that?
Yeah, so I spent a lot of time working with Pioneer on a validation project, and we've learned a lot about it since then. The calibration process that we use right now is fairly straightforward, and we've developed a calibration procedure that uses basically the stuff that the guys on the rig already do. And so basically looking at how they start up and tag bottom, we can use that to start the calibration process on the model. The big thing right now is that we're kind of reliant on downhole subs to give us data for our offset wells. What we want to do is at some point get to where we can look at just surface data and make good decisions based on that. So that is part of the calibration sort of model validation thing we're still working on. But we've got it down to where it's pretty straightforward. So basically it's one initial run to set things like bit friction, and that's gauge friction and face friction. And then we have the whole friction parameters, and we're starting to get a pretty good idea of how to set those properly. So it's not as time consuming as it used to be. We still have a lot of work to do there, but it's not something that's outside the capability of like an average user. So if you have some Adams skill and you've had Adams drill training, we can teach you how to do this calibration process, and it's pretty straightforward now.
Thanks, Jennifer. The next question is on the field data analysis. So the question is the Python scripts that were developed. So I'm guessing, Sarjan, this is the frequency mismatch script that you had highlighted earlier on. Are they developed in the Adams drill environment?
So the problem there was that the data sets. The directions the drill string moves. Sorry about that. The data sets are different depending on what downhole sub you use. So this is why the Python scripts were generated. But I guess it's something very easy for Adams to implement in its data evaluation parts. As long as they know what the data sets will look like, this process is actually very straightforward. And it can be also included, as far as I believe, it can also be included inside the Adams.
Great. Thanks, Sarjan. The next question is, how was the degradation of the bit and the motor set? The torque reduction factor?
For the bit, we are changing the bit's phase friction factors. And for the motor, it's a torque reduction factor as far as I believe, yes.
Yeah, so I can add to that. So at the bit, the torque that's calculated at the bit by the Adams solver is actually based on the friction factors. And so it's a functional model in the sense that we're not actually cutting rock. And so we basically manipulate those friction factors to model bit, some reduction in the bit efficiency. So that's how we do that. For the motor, it's a little bit more complicated, and it's essentially, we end up with some motor performance curves that model how the motor will respond. And what we do is we take the maximum or the max operating torque on the motor, and we basically scale that down to model a reduction in the amount of torque that the motor could produce for a given differential pressure. So that's how we model bit and motor degradation.
Okay. Thanks, Jennifer. The next question is, how do you model the bit itself? Do you take into consideration the bit profile, the bit gauge, and the possible, I guess, configuration, step gauge, back rake, etc.?
Back rake is not something that we have in there, but we do have, the bit model does take into account, for example, how many blades you have on the bit, how many cutters, and where those are located. So, for example, different manufacturers have different configurations for bits, and you have different designs for bits depending on whether you're in the vertical or the lateral and what kind of formations you're using. And drilling engineers have their own preferences. And so we have the ability to basically take manufacturer data for just about any bit and model that in Adams. And again, it's a functional model. We're not actually cutting rock inside Adams. And so what we want to do is create a model that has all the characteristics we need to get the right behavior for that particular bit. So one of the things that we're looking at is, what kind of frequency does that bit generate? So, how many blades are on the bit will influence that. So we want to make sure we get those details right when we model the bit. And we can do that inside Adams drill.
Okay, perfect. Thanks, Jennifer. The next question is, how user-friendly is the software? Tools to pick and assemble, or would you need to enter the complexity of the parent Adams tool in order to implement models such as this?
Yeah, we probably should have actually had something in here about Adams drill kind kind of a quick demo there, but basically you interact with Adams Drill through Excel. So it's some customized Excel worksheets, and you build the BHA inside an Excel worksheet. We use a database structure that's, we took a page out of the Adams CAR database, where all of these components are basically pre-built, and you pick the components you need to build your BHA, and that's how you do it. There are some rules that you have to follow, but they're pretty straightforward, and we have training available that helps you learn how to use that pretty quickly. So if you can use an Excel spreadsheet, you can build a BHA in Adams Drill.
Okay, thanks, Jennifer. There's a question about, I think you addressed this when we were talking about the real-time simulation capabilities. So what is the lead time to perform one set of simulation? I'm guessing, excluding the calibration part, how long does it take to perform one set of simulation?
It depends on, I mean, the
Jen.
salt is the biggest chunk of that. At least after you get comfortable building a BHA in Adams, it's really the solver time. And that depends on how long the drill string is. But in terms of just building the BHA, if all your components are already built, you're just picking them from a library, it's really straightforward to build it basically as fast as you can pick parts and put them in the spreadsheet for the BHA builder. And then the only other thing is you have to set up the event file. The event file includes the whole file. That can take a little bit of time to build, depending on how detailed you want to make it. And when I say building it, it's basically making decisions about friction factors and overgauge. The rest of it's pretty straightforward. The event file, if you know how you normally tag bottom on a rig, you can set that up in the event file pretty quickly. And then you hit go, and it'll build it and solve it for you.
Yeah, to add to that, for example, the well here that I modeled with the vertical, so it didn't have too much of complexity, and the depths were not too deep. So the models were taken around only 15 minutes or somewhere around 15 to 20 minutes. The other case where we have the horizontal at, for example, 13,000 feet, where you also pass through the curve section and you're in the lateral, those took a little longer. I guess it was around 30 or 40 minutes. Kind of more specific numbers.
Okay, all right, thank you. Thank you, Sarjan. There's a question about, I'm not really sure if I'm reading this right. How are you modeling well bore tortuosities?
We have the planned hole data. So, drilling engineer gives you the planned trajectory, and you can use that as the initial start point and just model the whole file using that. Later on, when you get survey data, you can go back in and update the whole file using survey data. And then when I was in the validation, we had the advantage of having some sonic caliper data. So it was really fine details about what the trajectory of the well was. I was able to use that for some of the wells when I had sonic caliper data. So it's really up to, how much information do you have about the data or about the well, and you put that in when you model the whole file. Now, the other thing is we do have a method of introducing artificial tortuosity based on what we think the tortuosity is going to look like. And that's just basically take the planned data and applying this artificial tortuosity generator to it, and then producing the whole file based on that.
Okay, all right, thanks, Jennifer. So there's a question about the simulation process itself. Is it simple enough that we could provide a part of the simulation procedure?
I don't know if we have a flow chart of the simulation procedure. I'll have to check. I know that we have some training materials for it. So if someone is interested in having us come out and do training, we can certainly illustrate that process for you.
The next question is on statistical analysis. What statistical analysis tool was used here to process data, the simulation data?
I wrote my own scripts on Python for this. So I did not use any statistical tool.
I think we covered. I think we've covered most of the questions here. I don't. Questions coming in. So thanks again, Sarjan, for this presentation, and thanks Jennifer for being a panelist and answering our questions, and thanks everyone for attending. So what we'll do is we'll all a copy of the presentation with the recording of the webinar, and with a contact email that you could use to ask us any questions. And please look out for more informative webinars on this particular topic that we'll be announcing soon. So with that, I'm going to end the webinar, and thanks again for the great presentation, the question and answer session.
Hemant, I wanted to just let everybody know if anyone has any additional questions about Adam's drill, or interested in having us come out and talk to them some more, please reach out. And if someone has questions, you can go ahead and forward that on to me as well.
When we send the recording and the presentation out, I'll include your email as the contact point, Jennifer.
All right, sounds good.
Thanks again. Bye-bye.
Thanks, bye.